In this video, we're going to look at the simple ideal decomposition of semi-simple Lie algebras. To begin, we're going to introduce the definition of a direct sum of ideals. We say a Lie algebra L is the direct sum of ideals I1 through In if L can be written as the vector space direct sum of I1 plus I2 plus ... plus In. So in particular, here we have the pairwise intersection is just the zero subspace. Of course, traditionally, we use the O plus to denote this direct sum. An important remark is that by the ideal property, I bracket with L is always contained in I, and so if you take any two of the ideals here and bracket them together, it's going to be contained in both I sub j and in I sub k. However, I sub j intersect I sub k is equal to 0 because this is a direct sum. And so we have that the bracket between any two ideals is equal to 0 if the ideals are not the same ideal. And so hence, we can view L, if it can be written as the direct sum of ideals, as just taking these different ideals and piecing them together, because there's really no interaction between them other than the fact we're adding different components together. And what's very nice is that the semi-simple Lie algebras decompose in this very nice way. That is the theorem we're going to look at next. So, theorem. If L is a finite dimensional semi-simple Lie algebra over an algebraically closed field of characteristic 0, then there exist simple ideals I1, I2, In such that L is the direct sum of these simple ideals, and every simple ideal of L is represented by one of these I sub j. Furthermore, the killing form of I sub j is the restriction of the killing form of L to I sub j cross I sub j. And so the way we're going to prove this is to start generally just by taking some ideal and then considering its orthogonal complement and then realizing L is actually the direct sum of those two pieces, and then from there we proceed by induction. So let's start the proof. So let's see. So let I be an ideal of L, right? Our claim first is that the first claim is that I perp, which is equal to everything in L such that kappa of that element with everything in Y is equal to 0. Yeah, everything in I is equal to 0. So for all Y in I, right? And our claim is that this thing is an ideal. And so this is pretty easy to see, right? If we want this to be ideal, that means that for all Z in L and for all X in I perp, we should have X bracket Z is an element of I perp. And so that's precisely what we're going to show. So consider any Y in I, and we have the following: kappa of X bracket Z with Y is equal to kappa of X with Z bracket Y. Now this is the associativity property we saw in the last video. And so this is equal to kappa of X with some Y prime, where Y prime is equal to Z bracket Y. But more importantly, this Y prime is an element of I because I is an ideal. And since X is an element of the orthogonal complement, this is equal to 0. And so we have kappa of X bracket Z with Y is equal to 0 for all Y in I and for all Z in L. And so we deduce that X bracket Z is an element of I perp. And so that means I is an ideal. Or excuse me, I perp is an ideal. So that's pretty easy to see. The next thing since we were trying to show that L is the direct sum of I and I perp, we want to show that the intersection between I and I perp is equal to 0. This is because we're using an implicit fact from say your earlier studies in linear algebra, which is that if you have a symmetric bilinear form, say kappa, so because kappa is symmetric, we have that dim I is plus dim I perp is equal to dim L plus dim I intersect I perp. And so this is because of this. This is just a course in symmetric bilinear forms. We'll show this. I won't prove it here, but I hope this is familiar. And so we're going to use this result. If we can show that I intersect I perp is equal to 0, then we're done. Because then we have dim I plus dim I perp is equal to dim L, and so that means I direct sum I perp has to be L, because they have no intersection. And so how might we show this? Well, this is where Cartan's criterion comes in, and this is why we need our assumptions on our fields. So if you have I intersect I perp, consider x comma y in I intersect I perp, which I'll call, I don't know, we'll call it A, because I don't want to write this over and over again. And so we have that kappa of x comma y is equal to 0, because if we view x as an element of I and y as an element of I perp, even though they're both contained in the intersection, we immediately deduce that this has to be true. And so that tells us the Killing form restricted to A is uniformly 0. And so that's actually a stronger condition than what we need for Cartan's criterion. Recall that Cartan's criterion, you'd only need to show that that's true for things in A with A bracket A. But here we have it, the Cartan, the Killing form is 0 for everything in A, regardless of what we choose. And since it's uniformly 0, we can apply the criterion to deduce that I intersect I perp is solvable. And so this arrow is Cartan's criterion. All right. And so, of course, what does it mean if you have a solvable ideal in a semisimple Lie algebra? It either means you're not semisimple, which doesn't make any sense, or you're 0. And so we deduce that I intersect I perp is equal to 0. And so it follows immediately from our dimension formula up there that L is equal to I direct sum I perp. And so now we have this. So the idea is to now just pick a minimal ideal and then consider the orthogonal complement. The minimal ideal by minimality is going to be simple, and the orthogonal complement is either simple, 0, or it's not simple. If it's 0, we're done. If it's not, if it's simple, we're done. And if it's not simple, we just proceed by induction. So let's actually verbalize that. And so consider a maximal or minimal ideal I sub 1 of L, right? Then we have that L is equal to I sub 1 direct sum I sub 1 perp. By the minimality of I sub 1, this is simple, so we can now ignore that piece, and now we just look at I sub 1 perp. And so if that's 0, we're done. L is just simple, and so that's fine, because simple Lie algebras are also semi-simple. So, or this thing is another simple piece, in which case we're done, or it's semi-simple, it's not simple. And in particular, it has to be semi-simple by the semi-simplicity of L. Otherwise, it wouldn't make any sense. There would be a radical for this, but not for that, which would be absurd. And so we can proceed by induction. To say L is equal to I sub 1 direct sum I sub 2 direct sum ... I sub n. And so the key thing here is that we said that L has finite dimension, and so that's why this process will terminate. All right, and so we have now shown existence, but we also need to show uniqueness, and so that's kind of the second part of the proof here. So uniqueness. This is pretty easy to see, right? So we want to show that if you have some simple ideal, let's say I is a simple ideal of L, then we want to show that it's contained in a list, so it is one of the I sub j. And so the way we're going to do this was by just using our existence formula. So we say I bracket L, right, is going to be contained in I because of the ideal property, but because I is a simple ideal, it's actually either equal to I or it's equal to 0, right? You can't have any ideals in a simple ideal except for the trivial ideals. It's not equal to 0 because that would mean we have a central element, and of course a semi-simple Lie algebra can have no center, and so we eliminate that possibility, and so we have that I sub L is equal to I. Okay, perfect. Now we can use our decomposition here and say this is also equal to I brackets with I sub 1 direct sum I sub 2 dot 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 so I sub n, and so this is going to be equal to direct sum. So I'm just going to use this notation to save time, and this is I sub, right? So we just kind of rewrite it in terms of bracketing I with each individual component, and so by this result, this thing is equal to I, right? And so by the simplicity of I, only one of these terms can stay, otherwise I is not simple. And so let's say it's j, that j is the term that stays. So then we say this is equal to I sub I bracket I sub j, right? And so by the same logic above here, this is contained in I sub j because I sub j is a simple ideal. However, it has to actually equal I sub j because I sub j is simple. And so it's either 0 or it's I sub j, and it's obviously not 0. And so that shows that I is equal to I sub j. And so I is a simple ideal, then is one of the I sub j. So that shows uniqueness. And of course the last statement follows immediately from lemma 5.1 in the last video. So yeah, so we know this right away. There's nothing really to be shown. Let's scroll back down here. Okay, so that's the theorem. And so what's beautiful is that we've changed our problem from studying simple Lie algebras, semi-simple Lie algebras, to classifying the semi-simple Lie algebras. And we already looked at some of the simple Lie algebras. We didn't show they were simple, but we looked at some of them, which were the type AL, type BL, type CL, and type DL. And then there's also a few more types. There's exceptional types, and there's an F type, and there's a G type. And so these are all the simple Lie algebras, and what this theorem says is, well, if you have a semi-simple Lie algebra, then it's just the direct sum of these simple Lie algebras. So it's a very nice theorem. And so we've reduced our problem to studying the simple Lie algebras. There is a corollary, and so these are some results that follow really quickly from our theorem. So let L be as in the theorem, then L is equal to its derived algebra. This follows immediately from the fact that if you have a simple Lie algebra, it is equal to its own derived algebra. Otherwise, it would have an ideal, which would make sense because it's simple. And so then you just write L as its as the decomposition of simple ideals, and then by the fact that they're disjoint pairwise would force you to get the following. This would end up equaling I sub 1, comma I sub 1, direct sum I sub 2, comma I sub 2, dot dot dot, up to I sub n, comma I sub n. But of course, as I said earlier, by simplicity, this thing is I sub 1, I sub 2, and so on. And so that's where we get, so that would be equal to L. Okay, let's actually jump to, so this is verified. Now let's jump to 3. All ideals of L are the direct sum of simple ideals. Well, that actually follows immediately from our theorem. We actually already showed that in order to show that L is the direct sum of simple ideals. So that's done. And then 2, all ideals of L and all homomorphic images are semi-simple. Well, the first part, all ideals of L, that follows from the fact that it's the direct sum of simple ideals. And then the second part follows from the first isomorphism theorem. And so this is done. I do encourage you to explicitly write this stuff out, but it's not too hard to see. All right, so that's enough for that. I just want to take a slight detour and just talk about some conditions on the base field that I felt like I talked about a little bit, but I didn't elaborate enough. And so just to make it all clear, so we kind of looked at 4 major results that had names. And so the first one was Engel's theorem. And so the condition on the base field is there is no condition. And then we realized if we wanted some more information, we have to be more strict. And so for Lee's theorem, we forced characteristic 0 and algebraically closed. For Jordan decomposition, we only required algebraic closure. And lastly, for Cartan's criterion, although we proved it needing both characteristic 0 and algebraic closure, we only actually need characteristic 0. And I think I linked to some notes that showed how you could actually construct, by looking at the field extension, the algebraic closure, and working with that. And so that's kind of the summary here. And so because we needed Cartan's criterion to prove our structure theorem here, our decomposition here, we require characteristic 0. And so I hope that clarifies any potential misconceptions regarding the conditions on the base field. So that concludes this video. Thank you for watching.